welcome to Earth Science, everybody. So let's look at this duck here. This is going to feel like we're not doing Earth Science, but we are. Looking at this duck, is there a way that you could tell which way that it's swimming other than the way that it's facing? If I was better at Photoshop, I'd like have it have two heads or something. I don't know. So, it's facing that way. We know it's going that way, right? But there's other hints that are revealed if you look carefully at the water that will tell us which way it's going. And in fact, you're going to have to explain what's going on in just a minute. So let's check it out right now while you got me talking. I know, even if I've never seen a duck before, that this duck is going this way because what's happening is that as it sits in the water and like bobs up and down, it sends out waves. But the thing is that as it does that, if it's moving in this direction, it's catching up with the very waves that it sends out. There's this term we're going to throw around called wavelength. And here in Earth Science, you'll need more when you get to physics. Actually, this really is it anyway. It's how far is it from one crest to the next crest, which you could also do from trough to trough, but we'll do it from crest to crest here. What's that distance right there from one crest to the next crest? What I'm seeing here is that since the duck, as it's emitting these waves, is catching up to the very waves that it emits, the wavelength here is smaller. Whereas towards the back, and I admit that it's not outstanding in this picture, the wavelengths are maybe like here and here. Since it's moving away from those, the wavelengths on that side are getting longer. That's called a Doppler shift. And it happens in all types of waves. Waves in water, sound waves, light waves, whatever waves you can think of. This will happen if the source of the waves is moving. It will shorten the wavelength in front and lengthen the wavelength in back. So, right here, press pause. Tell me which one of these two diagrams is correct and why. That's your job right there. Shouldn't take much. Press pause now. And once you do that and come on back, let's, again, please don't go on to the next section until I see some words here. I'm watching you virtually online. So how does Doppler duck help us unpack what's going on with what we're doing here in Earth Science, which is the universe, right? We're trying to figure out how the universe got here, when it got here, and how we humans have been able to figure out some of this. So another homework assignment that I usually give that you could honestly do, if you go to YouTube and type in Doppler train, you can kind of do your homework in your seat right now. But I usually say go outside and listen to a car as it drives by. Because a car is emitting sound waves. It doesn't have to be a police car. It can be a car just with an engine will be emitting sound waves. Or if they're blasting tunes, you can do this too. As it comes at you, it catches up to the very sound waves it emits, so the wavelength decreases. Whereas as it drives away, the wavelength increases. Okay. So I probably shouldn't try to improvise and find some of this online as we go, but old habits die hard. Oh, and we got to watch ads. You probably already watched an ad to get to this. All right. So there we go. As this thing moves forward in one direction, it's catching up to those waves. Now it's moving forward in the other direction, so it's catching up to those waves. If you're experiencing that as you sit still, you're seeing what's going on with Doppler shift. Okay? If it's a sound wave, you hear that as pitch. So again, if it's somebody with music and you're and you listen to a lot of music, you have sensitive music ears, you can hear pitch. You'll hear the pitch go a little bit high as they approach you and a little bit low as they go away. Or if it's a car, what does it sound like as it comes at you and then as it goes away? The engine of the noise out of the engine sounds about the same to the rider, but since you're sitting still and experiencing the shift in those waves, you experience the Doppler shift. Okay. So if Doppler is a thing, I guess we should jot a few notes, right? Small wavelength, high frequency. So, I mean, really, we got it. It's already on there, but this is a little smaller here. Moving toward us. That will happen. The wavelengths get smaller, the frequency gets higher. Don't worry about frequency necessarily, but that'd be why you hear it as a higher pitch. Whereas if over here we'll type as it's moving away from us. Here it is a lower pitch, a longer wavelength. Okay. Most people don't argue with that too much. I think a lot of times by the time you're in 10th grade, you've experienced that. Let me pull up a train one real quick. I'm going to do your homework for you. So I guess what I'm not sure of is if I play this, if you guys are going to be able to hear the audio like YouTube through another YouTube video. But hey, here it comes. Check it out. So if you heard that change in pitch, that's the deal here. That's what we're trying to work on. If you couldn't, again, just search Doppler chain. A whole bunch of them pop up. Nice and easy. All right, why are we babbling about this so much? Next, what we got to see is that this doesn't only happen with sound or with duck ripples. It happens with every kind of wave. So we're going to get into the spectral analysis thing, which is like opening the door to some very difficult stuff. I was going to do a lab on this year. This was going to be a new lab I do. This is one I found online that I would have adapted a little bit, but it's tough. This is hard stuff. I mean, very accurate plotting with a whole lot. And really what it gets to is like stuff that's in physics. It's not necessarily in earth science. I think it's a little too complicated for what we got to do right now. I think we can wrap up all of that without the lab just by saying, hey, here's what this thing is, and here's what it is. And I'll have these little tubes up front. If you want to try to play with them, you'll look through them and you'll see like a little rainbow. They sell these as like kids' novelty glasses, like little glasses. They look like 3D glasses almost, but they make everything look like rainbows. That's kind of doing essentially the same thing. It's taking light and bringing it down into its component colors, which is the rainbow, Roy G. Biv, right? What we've noticed is that certain elements give off certain specific patterns, like a fingerprint, more or less. And that's what part of this lab would have been like, right? Is like discovering these little fingerprints right here. Keeping it simple, I'll just say, hey, that's a thing, that happens. But here's what we notice is that these fingerprints do something very specific because the source of the stars, they're moving, they're in motion. And that does a Doppler shift, this whole thing, this train thing, but it does it with light. So if changing the wavelength and the frequency over here changes pitch, if you change that with these emission spectra, you actually change color. You change the color that you would observe. So if we want to do spectrum analysis and wrap a whole lab up in one sentence and not worry about doing it, stars have specific fingerprints. And I put that in quotes. Like they're not, stars don't have fingers, you know? But what I mean by that is like, but based on what's going on inside of them fusion wise, they have a very specific pattern that they would emit if you use the right equipment to detect it. It's fairly simple setup. This isn't like you need the Hubble telescope and a lot of fancy equipment. You can do this with these little tubes they have in their room. So they have these certain fingerprints. And what we notice then, if we combine these two ideas, is that should a star be moving away from us, which is what we observe, all of the light, those patterns of light, those fingerprints shift to the red end of the spectrum. All right. So now is a good time to bring up the reference table. So I'm going to pause. All right. Here on this reference table, we've got this guy right here, which we'll really spend more time unpacking another time. For right now, visible light goes by the rainbow, and it's Roy G. Biv, like backwards on this one compared to the way you usually say it, but that's okay. With the increasing wavelengths, longer wavelengths that way, and the shorter wavelengths that way. So let's go back to sound. I know this is maybe getting slightly repetitive if it's making sense, or even the duck. As the duck goes away, if you're observing it on this side, you see a longer wavelength. With sound, as the police car drives away, if you're observing it, you're experiencing a longer wavelength, a lower pitch. So with stars, if the stars are moving away from us, we observe a redshift. Now this is going to be the word. This is like the $100 word here of all the babbling I'm doing here. Stars moving away gives us red shift. The regions will like to ask about the Doppler shift occasionally, very rarely emission spectroscopy stuff, never ducks, but redshift all the time. I'd say It's on almost every test within the first 5 questions. There's a question about the formation of the universe. And our understanding of that has been based in this redshift. So if however long this video is, turns into mush in your brain, redshift, redshift, redshift. That's the thing. Okay. So let's just note what it shows us and think about this. So a redshift shows us stars move away from us. We've observed this. We see all over the place stars are moving away from us, which gave us the idea that we live in an expanding. Now, if you're really thinking about this, I'll tell you where I struggled with this as I was learning this even in college. As I said, if all of the stars are moving away from us, doesn't it feel like we should like then? Does that mean that we live right in the middle of the whole entire universe? Because if so, that'd be kind of human centric viewpoint of the whole universe. What are the chances with all of this outrageous amount of space that Earth is the thing that's right in the middle? That doesn't seem too likely to me until I read about this demonstration right here. So if I take this balloon and pretend it's a universe, I blew it up a little bit to represent a young universe, and I'm going to take a Sharpie and put a bunch of dots all over this balloon and say these dots represent other stars, other galaxies, whatever. Other little things we see in the night sky. All right, pick one of those. That's where you live. And here's why it doesn't matter where you are in the universe. If I take this universe and expand it further, continue to expand the universe, which is what we see happening, what happens to the distance between you and your neighbors? No matter which one of those you picked as your house, you got further from your neighbors. As the whole entire universe expands, everybody moves away from everybody else. And it's what we observe. So um, this was Hubble figured this out, who said, okay, if we see a constantly expanding universe, we can observe that through this redshift deal. And I like played that tape backwards, put it on rewind, then the universe would be getting smaller, 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 and smaller down to a point. So he says, well, I think that the universe had some kind of beginning, some kind of point, and then boom, from there was this big bang, and it's all been continuously expanding from there. A cool idea, a clever idea, a good insight. Was all of this absolute proof that that's a thing? No, not yet. It wasn't enough. But this was the beginning of giving us our Big Bang Theory. And again, this is the thing. So I'm glad you're still watching. This is the thing that leads to Big Bang. Now, in the next set of notes, I'm going to show you the standard. I'm going to say, here's exactly what they ask, and we're going to practice those. These are a few of the questions that do pop up. Number 1, number 4, number 8, number 2. You see, it's pretty early in the test. It's like a consistent pattern that they do. These things would represent those like emission spectroscopy lines that are confusing things. But if you got these, what happened down here? They all shifted towards the red. They don't get closer, they don't get further, they just shift over towards the red as this universe expands. Were the universe contracting, we would see everything getting closer to us, the wavelength would get shorter, and we would call it blue shift. But we don't observe that on a large scale. We observe a whole heck of a lot of redshift. All right, so I'm going to have you guys try. There's 4 questions here. I want to make sure they're doable. I think, and they're a little repetitive. Yeah, very doable. Okay. I mean, if you do those on there, then we're gonna have another note sheet for another idea, and then there will be a classwork that will just like use these questions. So do them, and then just kind of save the answers, and you will plug those in later. All right. Redshift, expanding universe, Big Bang. Deal? Thanks, everybody. We'll talk to you soon.